We're happy to have Alethea Barbaro. She's a assistant adjunct professor at UCLA. She's going to talk about gang dynamics, mathematical models for gang territoriality and rivalries.
Thank you very much. I want to thank you all for having me here, first of all, because it's really nice to be back at UCLA. I grew up in Amherst. So what I'm going to talk about is very different from some of the earlier talks today. I do agent-based modeling mostly. So I'll talk a little bit about what agent-based modeling actually is. I also managed to get a little bit of laryngitis on the plane, so if you can't hear me, please let me know. And if I say, I have a microphone if I need to use it. Is it hard to hear in the back? Okay. I guess I'm going to probably have to adjust my volume somewhat. Is that better in the back? Yeah. Yeah, if you can't understand what I'm saying because of my laryngitis, just ask me to repeat. And if you have any questions, I also don't mind taking questions during the talk. So feel free. So what I'm going to talk about today is I'm going to talk about a couple models I've worked on while I was at UCLA. So I'm going to talk about a model that we made for gang rivalry formation. So looking at how a gang rivalry network might evolve using agent-based models. And then I'm also going to talk a bit about gang territoriality and a spin model for gang territoriality. So looking at how graffiti and how graffiti might essentially create, allow gangs to create a territory. So this is the reason I'm interested in gangs. What you can see is on the left, you see a map of gang injunctions in Los Angeles. So Los Angeles is the area that is white or colored in the map on the left. The areas that are white, there's no gang injunctions, but the areas where there are colors, it means there's a gang injunction there, which essentially means that there's enough gang activity that they can justify a restraining order against a gang. So if a gang member's there, they can stop them, they can take down information about them. It's essentially a restraining order against a gang. And you can see in the middle, particularly in the middle of, let's see, is this a pointer? Is this a pointer? Ooh, that was bad. If you can see in the middle of that, in the middle of the map there, right above my head, you can see that there's this whole rainbow of colors. That means that there are a whole bunch of different gangs. So each color there is a gang, and each area there is an area where the gang is not allowed to go. The data that I work with comes from Hollenbeck, which is a particular region in Los Angeles. If you look here, this is a close-up of Hollenbeck, and you can see the Los Angeles map in the upper left-hand corner there, and the dark gray area is Hollenbeck. This is a really nice area because it's actually been well studied also by criminologists. So we have information about the gangs and the gang violence, etc.
Just a quick question for clarification. With the different colors where you have these restrictions, is that for that specific gang is not allowed to be in there, or all gangs, period, are not allowed?
It's that specific gang. Yeah, so essentially a gang injunction is a restraining order against a particular gang.
Okay. Thank you.
Yeah, sure. And so in Hollenbeck, we actually have, but in Hollenbeck, there's an orange spot, there's a blue spot, there's a pink spot, there's a green spot. There are multiple gang injunctions there.
Press the center button on
Center
there.
button, center button. Okay, so this is Hollenbeck right here. And you can see that Hollenbeck in particular is riddled with these gang injunctions. Okay, and this is the violence data for Hollenbeck. This is from data that we got from the LAPD. This is the violence data in 1998, 99, and 2000. You can see that towards the middle here, that's actually where a lot of the gang territories are. And there's quite a bit of violence there. Red, the orangish red is a lot of violence as it goes down to yellow, and then the green is just the background color. But you can see that this area right here is hot in all three of these years. And we also have an area here that's hot in all three of the years. So what we want is a math model that allows us to explore the way gang rivalries form in this area. And we want to look really at the dynamics of the gangs. The idea behind this is that we want to better understand how violence happens and what motivates violence in Los Angeles. And we know that in this model, space is going to be really important because we have these people and they're moving around through space, they're crossing freeways, they're thinking about areas that they're in, they're thinking about where other gangs are located. And what they're really trying to do is stay alive, right? So space is a really important component here. We have information from the criminology community. Okay, so we know from the criminology community that each gang has a central space called the set space, okay? And that the gangs form rivalries with one another, and that these rivalries evolve over time. And also that gang members tend to avoid the other gang's territories. So if I'm in one gang, I don't want to walk into the other gang's territory because I'll get shot. Right? So there's this dynamic, and actually when I came into this project, that's not the way that I thought it would work. I thought, oh, well, when I go beat up the other gang, I'm going to go try to get them to beat me up, but no. People tell me that it's the exact opposite of that. You try to avoid your rival's territory. And so we thought about how we could approach this model, and an agent-based model is a really nice approach. An agent-based model essentially is thinking about particles moving around in space, okay? And each particle we think of as a person, an agent. And this person has things that are motivating it and rules for how it wants to move, okay? And the nice thing about this is it's a really accessible kind of model for criminologists, also for biologists. It's used in a lot of areas. But for us, it enabled us to talk to the criminologists and say, does this make sense? Is this a movement dynamic you support? And what we could then do was sort of adjust the rules for each agent so that the rules reflected the way the gang members actually move around in space. And the flexibility, well, an agent-based model allows for the flexibility of incorporating different movement dynamics as you're going through. So you can say, run a simulation with one behavioral dynamics for the entire set of agents. And then you can change the dynamics and run another simulation. So it's really flexible. You also can easily incorporate geographic information. So if there's a boundary there, if you don't want to cross a river, if you don't want to cross a highway, you can actually incorporate that into the model very easily. And and you'll see what we did actually was create a model that allowed for an evolving rivalry network. Rather than just looking at space and saying these rivalries exist for all time, we could actually create a rivalry network that would evolve over time and change, which is something that makes sense in the real world system that you don't necessarily get from just a geographical, sorry, just a geographical graph generating network. Okay, so this is the actual network that they see in Hollenbeck. Each one of these nodes here is a gang, okay? And each one of these connections between nodes means that there's some rivalry between the two gangs. Okay? So you can see there are a whole bunch of gangs here. And in particular, there are also some gangs which serve as a separation between one group of gangs and another group of gangs. So, like Hazard, right here in the middle, is separating one group of gangs from another group of gangs. So what does this look like when we look at it in space? Next thing to think about. When we actually put it into space, we see that the Hazard is right there actually, and it's separating the northern gangs from the southern gangs. Okay? And when we put it in space, we can look at another few things. This is actually the LA River here. River. It's really a whole bunch of cement with little dribbles down the middle. But it's the LA River, and people don't usually tend to cross it. So that can serve as a kind of boundary for our system. This here is a freeway, and again, people don't tend to cross that freeway so much. Here, this is actually just, these boundaries are actually just where Hollenbeck ends. So they're not actually physical boundaries, but what was interesting is that most of the rivalries that the criminologists observed, and all of the ones they've reported in this paper, occur inside Hollenbeck itself. So we can think about Hollenbeck almost as a closed system in terms of the gang members. There are 29 active gangs in Hollenbeck that we were working with, and again, we referred to this paper for the details about where the centers of activity were, and also which rivalries existed. And right here what we have is we have the node representing the gang placed at the point in space where the paper said the gang has a center of activity. So again, that's where the spatial components come in. Oh, I don't. Okay. So there are a couple of different ways of thinking about creating this kind of network model. Okay. We have graph generating methods, such as maybe the geographical threshold graph, and we have agent-based methods, which clearly are the ones closer to my heart. Okay. But we're going to look at both of those, and when we have agent-based models, we actually can use different behavioral dynamics for the particles, for the agents. So when we looked at it in our paper, we looked at the geographical threshold graph and the best fit we could get to the rivalry network for that. And then we looked at two different behavioral rules. So geographical threshold graphs are a way of looking at a network that's embedded in space. And with a geographical threshold graph, you randomly assign weights to the nodes. Okay, and then you create an edge between two nodes if some function of the weights of those two nodes divided by the distance raised to some power is less than or equal to a threshold. It's a method from graph theory, and what we did was we actually looked at a specific realization of a geographical threshold graph. So we figured that a rivalry was more likely to form if a gang had more members in it, essentially. So we knew how many gang members were at each of these nodes. We knew how many gang members were in each gang. Okay. And we used that as our weight for the gang. And then what we did was we looked, so our function f was just the product of the sizes of the gangs. And the distance, this d, is just the Euclidean distance between the two. Okay. And we used beta equal to 2, which is a common choice. And what we did was we thresholded until we had the same number of edges as actually exist in the actual observed network. And this is the fit that we found with the geographical threshold graph using that. And this on the left is again the observed network. So you can see that some of the features are reasonable, right? We still get this division with hazard dividing the north and the south. We still get this nice little area in here, right? But we're much too connected up in here. Okay, so it's picking up on rivalries that don't actually exist. But still, it's a reasonable fit. It's a reasonable fit. But one thing that we don't get here that we could get from an agent-based model is where the gangs would actually clash. Okay? So if we create a geographical threshold graph, we get one graph, and that one graph is the only one we're ever going to get. It's not going to evolve, and we're not going to get any information out about where events that caused the rivalries might have happened. Okay. So we thought about using an agent-based model, and we started with just thinking about diffusion. I'm hoping you guys can see the red over on this side. Okay, so what I have here is I have a rough plot of Hollenbeck. You can see this was in the beginning when I was just thinking about the problem to start with. Okay, and what I have on the left is all 29 gangs, okay, with the number of gang members that are in each gang. And I started them at the center of their activity. I started them at their set space. And then I let them just diffuse on a lattice. Okay, so they're just doing regular diffusion here. And when agents from, say, the purple gang encounter agents from the mustard-colored gang, okay, then a rivalry is formed between the two. There's an entry in the rivalry matrix. Okay, and those entries in the rivalry matrix are recorded over here. So what you're seeing on the right here is essentially a record of agents from different gangs having come between a certain distance of each other, within a certain distance of each other. So you can see here we're getting the same kind of thing that we're getting from the geographical threshold graph, which kind of makes sense, right? That's kind of what the geographical threshold graph is doing also. And again, it's pretty connected in here, but we're getting the right kind of structure here. But if you let it evolve, you get way over-connected, right? And everybody's just everywhere, you're just confusing. That doesn't look so great. So clearly, if you're thinking about an agent-based model, you're going to want to think about something beyond just diffusion. You need to incorporate some other dynamics. So what we decided to do was a biased levee walk with semi-permeable boundaries. Okay. So in our movement dynamics, the agents move in free space. So we stopped working on a lattice. They're moving in just regular plane. Okay. And they're moving according to a biased levee walk. And I'll talk a little bit about what we mean by that. Okay. But they're choosing the direction of the bias according to where their own gang has its center of activity and where their rival gangs have their centers of activity. So like I said, an agent will want to avoid the rival gang's territory, and it'll also want to go home. And we also have agents having some probability of crossing a boundary, but we don't want them to just automatically cross. So in LA, there's a lot of freeways, and when you encounter a freeway, you're less likely to actually cross to the other side. I've noticed this with myself. And the 405. You don't really ever want to go under the 405. It's not really fun. There's traffic. It's awful. So, so we incorporated information about the freeways also into this model. And then in order to make the interactions happen, we thought about what happens when different gangs get close together. Okay? So when different gangs got within a certain radius of each other, which worked out to about half the city block, okay? Then we said that an interaction has occurred. We increased the rivalry between those two gangs. And then at the end of the simulation, we excluded rivalries where the number of interactions was mutually insignificant. Okay? So if I had one interaction with that gang and like 50 with this one over here, I don't really care so much about my interaction with that gang. I'm not such a rival with that gang. So that information is incorporated at the end of the simulation. In terms of using a biased levee walk, the reason that we want to do this is there's actually some support in the literature that says that that people, when they're moving in an environment, in an unconstrained environment, their movements are like distributed like a power law, and if you have obstacles, the jump lengths are more like a bounded power law distribution. Okay, so and also then when we're talking about the movement dynamics, people definitely frequent certain locations. We said it was their set space for their gang, but there are probably also another few places that people go. So, and then we also had gang members avoiding rival gangs' territories, and we heard from the criminologists and the Hollenbeck Gang Division that they actually do this. So when we were choosing the jump length, so essentially what we have is we have particles moving around in space, and we have a whole bunch of them. And here's Hollenbeck. And we choose one. In order to make them move, we just pick one particle to move. Okay? And I say, okay, I want this particle to move. Now I have to figure out where it wants to move. Okay? So I'm going to have to choose a direction that it wants to go, and I'm going to have to choose a distance. So when I'm choosing the distance, I'm picking actually from a bounded Pareto distribution. So that's what's written up here. And for the bounded Pareto distribution, you need a minimum jump length and a maximum jump length, the bounded part, and then you have a few parameters, like the K. So you have K, X min, and X max that you have to choose. And what that's going to do is tell me what distance I want to jump. So So I sample from that distribution and it gives me some length. Okay. And then I have to choose a direction that I want to go. So when I want to determine my angle that I want to go in, right? I actually want to think about where the other gang territories are of my rivals. So if I'm here, but my home is here, okay, and then I have a really strong rivalry with somebody here, and a really strong rivalry with somebody here, I'm going to want to go towards home, and I'm going to want to go away from those two. Okay, so I'm going to probably end up going something like that. So that's all this slide is telling you. And what we did was we made the desire to move away from your rival's territories depend on how strong the rivalry was between you. Okay? And also the distance that you were from the rival. So if you're really close to the rival, we wanted to move away really a lot. Okay, so that actually had a bigger weight when we were choosing which direction to go. And then what we did was we took a von Mises distribution, so we said, okay, this is the direction I want to go, but maybe I'm not going exactly in that direction. Okay. So we chose a von Mises distribution with the direction that we wanted to go already in there as the mean. And then we sampled from that distribution in order to pick the direction to go. And what this allowed us to do was essentially incorporate some kind of stochasticity also into the directional heading. And then when we were thresholding the rivalry, well, with the rivalry, essentially what we did is we summed up all the interactions that anyone in our gang had had with anyone in the other gang. So anyone in gang I with anyone in gang J. And then we divided by the total number of interactions that had happened with gang I, my own gang, at all. Okay? And that determined our rivalry strength. And then at the end, we thresholded. So we picked a threshold value to tell us which ones actually mattered. And when we compare the results we got from this, we have, again, the observed rivalries right here. Okay? We've already seen the geographical threshold graph that was our best fit. Okay? When we ran it with our semi-permeable bias levy walk network, okay, we got this graph right here. And when we ran it with just Brownian motion, but now we have the semi-permeable boundaries in there also, we got this graph right here. Okay. And you can see of these graphs, this one, this one, this one, and this one, right? This is actually visually the nicest match with this. Right? Because what we're seeing here is we're not getting those long-range connections. Okay? And we're over-connected right here. And we're seeing something really skewed with the Brownian motion network. So what we did was we did a whole bunch of different graph metric comparisons between the graphs that we got out of this simulation and the observed graph. We looked at the accuracy, we looked at different shape metrics, and we found that it actually performed pretty nicely, even when we looked at an ensemble of runs rather than just one. And we also found that we actually had a limiting behavior for the ensemble of runs. If we looked at, say, the graph density, we didn't have to look only at the graph density. You can look at a whole bunch of other metrics. I just picked graph density because it's here. So the actual density of the graph in the observed graph is this green line right here. And as we run our model, the average is this red line here. So you can see that the red line is actually asymptoting to the correct, well, close to the correct graph density. And then you can see the blue here. These are the density of the graphs for each run. So you can see what's happening here is the density changes as the run continues. Right? So you can follow the line. It's going up, it's going down. Right? Some of them are above the actual density. Some of them are below. But what we're seeing is something that's making reasonable sense. Okay. And if we look also at the number of edges that appear all the time, or the number of edges that appear at all ever, okay? On the left, these are the edges which always appear in every simulation we did for our ensemble. Okay? These are the edges in the middle. These are the edges that appeared at least half the time. Actually, half the time, okay, or more. And then these are all the edges that appeared at all. So what we're seeing here is that there are a lot of edges which don't occur, right? Like a connection between that guy and somebody down here. So there are a lot of edges which just will never come out of our simulations, or very rarely. But the nice thing about this is it shows that actually the model is fairly flexible, and you can get different graphs depending on how long you run it for. Things change. Okay? So that's a nice thing, because we actually know that the real system, when we're thinking about gangs in real space, real people, right? We do have that stochasticity in the network, so it's not fixed. And this is one of the things that makes this kind of evolving rivalry network simulation interesting, instead of something like the geographical threshold graph. Because we do have this flexibility, and we do have this stochasticity there. And also, when we look at the violence data, so again, this is just the violence data plotted again. What we have here is our simulation, and in our simulation, we looked at where all of these interactions occurred. Okay? And you can see that the largest density of interactions actually occurred in this area here, which is where we see the most violence. And we get some interactions, a fair amount of interaction up here, which again reflects this, okay, and a fair amount down here, which again tends to be reflected also in the violence data. So I'm not making any sort of contention that this is correct, but it does have promise in terms of looking and seeing where the violence is occurring. And also, one thing to keep in mind is that some of these edges that show up with our graph that don't actually exist in the observed graph, in the observed rivalry network, they could be there because we assume every interaction is negative between anyone ever. That excites the rivalry. And this isn't actually the case, right? You might have a girlfriend in a different gang, and you're not really gonna get really mad at her brother every time you see him, right? That would be really not very smart. So what we're doing here is we're making assumptions about the way people behave, and they're simplifying assumptions. But it could mean that some of the graphs, some of the edges we're getting that the actual observed network doesn't have, like say this one right here between those two. Those edges might be occurring because we're classifying every interaction as negative. Are there any questions here? Just because I'm going to move on to a different topic. There'll be more time at the end, too, I think. Oh, okay. I'm going to talk about the next topic fairly quickly. So another thing that I did while I was at UCLA is I looked at a spin model for gang territoriality. In this model, what I did was I thought about gang members moving around in space. Now I'm on a lattice instead of being in free space. Okay? And I thought about the agents moving around. I had red agents and blue agents. The red agents moved around and had a certain probability of putting down red graffiti. The blue agents, same thing. And then the red agents avoided the blue graffiti. And the blue agents avoided the red graffiti. Okay? And one of my advisors went through and said, oh, that sounds like something we could turn into something like a spin system, a spin model. Okay? And that's where this idea came from. We ended up looking at a spin model that was associated with the dynamics that I just described, using the idea of gang tags, gang graffiti, and we proved that this undergoes a phase transition as we change the parameter values. So essentially, I have something like a configuration of agents on a lattice. So here you can see red agents and blue agents. In our spin model, we had only a red agent, a blue agent, or no agents, so agents couldn't pile on top of each other. Okay, exclusion. And then I have gang tag, and the gang tag is also associated with the lattice point. And so when I put them together, then I have agents and gang tag. This agent is really happy because it's near a red tag. Okay. And same with this agent. This agent is a little less happy because it's got some blue nearby. Okay. And it doesn't like being near a blue gang tag. And so what we did was we designed a Hamiltonian that captured this idea. So we thought about a spin at each lattice point, which consisted of an agent spin, eta I, and a graffiti spin, gi. And the agent spin was either -1 if it was blue, 0 if it was empty, or 1 if it was red. And the graffiti was in R, and if it was negative, it meant it had more blue tag than red tag. If it was positive, it meant it had more red tag than blue tag. Okay. And the Hamiltonian that we came up with is right here. This term right here, this eta I gj, with this funny little symbol down here, means that we're adding up, we're looking at every pair of lattice sites. And we're looking at whether the graffiti at the lattice site matches, if the graffiti at the lattice site matches the agent at the neighboring site. Okay, so that's what this eta I gj is about. And we're saying if they do match, we want to increase negative H. Okay? And then we do the same thing, but at the lattice site itself. So this sort of accounts for the idea that the agents will produce graffiti. So the agents want to put down their own tag, and that's captured by that term. This term right here encourages there being agents on the grid at all. So 8i squared, if you have an agent there, that's going to be 1. So this actually encourages the lattice to be populated. And then this term right here discourages there being this difference between red tag and blue tag. So the difference between red tag and blue tag actually decays. Well, it's discouraged because of this Hamiltonian. And just briefly, I'm going to go over what we did. So the model, we proved that the model undergoes a phase transition as we vary J, K, alpha, and lambda. And I've had a lot of people ask me what a phase transition is. So a phase transition in our case, we looked at the agents being well mixed. So we looked at red and blue agents coexisting, sort of mixed up. And then we looked at red and blue agents being divided into different spots. Okay. So in one case, we're having a well-mixed phase, okay? And the other one, we're having a separated phase. And that's what I mean when I say a phase transition. So we're thinking about the system transitioning from being well-mixed to being segregated, from being well-mixed to having territories. Okay? That's why we started thinking about territorial formation there. And so for the outline of our proof, what we did first was we showed reflection positivity, which essentially says if I'm near you, I want to have, I'm more likely to be the same color as you. Okay. So we showed that with our Hamiltonian, the system has reflection positivity. And then we bounded the probability of bad pairs. Okay. And a bad pair is where agents were next to other agents that weren't their color. Okay. So if a red agent was either next to an empty site or a red agent was next to a blue agent. Those were bad pairs. Okay? And then we proved phase transition using a contour argument. If any of you have thought about the Ising model, you may have seen this before, but the idea is that there's a red agent, and there's a red agent, and there's a red agent, and there's a blue agent over here. Then somewhere between this red agent and this blue agent, there had to be a bad pair. Okay? If I have nothing else on the lattice, it would be right here. But maybe I have something else on the lattice, maybe it's over here. But the point is that there is a spot between here and here where there's a bad pair. And if you have red agents and blue agents, you can actually show that if you have a blue agent over there and you have an island of red agents, that you can draw a contour, a closed contour around them. And then you can think about the length of the contour and essentially prove the phase transition using a contour argument by saying that there shouldn't be this contour. And then we looked also at the mean field Hamiltonian. So in the mean field Hamiltonian, instead of thinking about just pairs, nearest neighbor pairs on the lattice, we thought about every lattice point being paired with every other lattice point. And we again, we changed the form of the Hamiltonian slightly by setting the J and the K parameter equal. Okay? And then this pops out. And and you can prove actually that a phase transition occurs here also. And okay, and the idea there is that you have a phase transition, you know where it is, and you can prove that one part of the phase transition is critical and one part is first order. So they're different kinds of phase transitions. And I'm going to stop with my research summary. So what I talked to you about today is gang dynamics, but you can actually use interacting particles for a lot of other things. So just for fun, I put some things on here. I've worked on interacting particle models for fish migration instead of gangs. Okay. So you can think about the way fish align and move through space. And then the fun part is you can think about the way that turns into a continuum. So you can throw more and more and more and more fish in until you have infinitely many fish, and then you can think about the surface of fish, and then let the surface of fish evolve. It's fun. It's really fun. So I've gotten into kinetic theory recently. So I have continuum limits for particle systems, and I've been working with people, mostly in Europe, on various kinetic models for these kind of particle systems. So agent-based models can be a lot of fun, and there's a lot of really exciting mathematics that I've been learning recently that is associated with it. So that's all. Thank you. Any questions? Yeah?
Yeah, I had a question about that. You had a graph in the first part of the talk that was on the graph density, or like the edge density.
Yeah.
And I was wondering, it seems like that graph density would sort of depend on sort of the parameters you chose for, say,
Yeah.
for the threshold for like, something being considered rivalry in that way.
Yeah, so we chose a certain set of parameter values, and we called that our model with a certain set of parameter values. And with that set of parameter values, we did these runs. So this is with a certain threshold and a certain minimum and maximum x and a certain k. Yeah, that's observant. So if we had chosen a different one, then we'd get a different thing. And actually, if we had chosen a different one, it might be totally wrong.
Just out of curiosity, did you select the values before doing the simulation, or sort of afterwards?
Yeah, so we selected the values not before doing the ensemble runs, but we selected the values by essentially fitting the parameters so that the accuracy metric was close for the run, and then we did an ensemble runs. Other questions? Okay. Well, thanks again.